Good morning, everyone. So I'm Maëlle Kabir-Kerek, and I'm going to talk about some work I'm doing for my PhD project. My PhD is led by GIPSA Lab, which is a laboratory of Grenoble here, about signal processing, image processing, and automation. And also led by a small engineering company of the area, Eurosystem. It's a company working on automation and industrial informatics projects. So this work is funded by Eurosystem and by the French Association of Research and Technology. And I also must mention Pascal Bellemin, who is the programming engineer of GIPSA Lab and has given me a lot of help for this work. So the content of this presentation, I will first introduce the context of the work and its objectives. Then I will present the system we are interested in, so that is substation for the power grid. So I will present the communication architecture and then the protocol itself. And finally, the last part is about the core work, the core ideas of this work. It's detectors for some attacks on our architecture, on our communication architecture. So I'm starting with an example. This is a picture of the 2003 North America Great Blackout. It was due to a defective state estimator, this state estimator was restarted, but the monitoring tool associated was not restarted. And added to that, there was a cyber bugs which blocked the alarm system for about 1 hour, depriving operators of any state information for 1 hour. And so this resulted into a cascading failure and finally into this great blackout. So this was not a malicious attack, it was an accident. But I chose this example to show how cyber vulnerabilities can impact the power grid infrastructure. Such a failure is possible because ICT, information communication technologies, are key to monitoring and control of the power grid. This is what we call smart grid. I guess you have already heard this word. So smart grid is the power grid with a layer of ICT dedicated to automation. So smart grid, power grid automation network has become very open and connected to very global networks. Smart grid deployment relies on the IEC 61850 standard. It is a standard entitled Communication Networks and Systems for Power Utility Automation. And the main purpose of this standard was to bring interoperability between different vendors' systems and to reduce wiring in substations. So the security, the intrinsic security we had basically has become lost because of openness. We lost isolation, which brought some security, and by the past we used proprietary protocol, and so we had some security through obscurity. But now protocols are based on Ethernet, as the previous speaker mentioned, and so we lost this obscurity security as well. So we mean dedicated security measures, and the point is that available ICS on the market don't have any security measure inside, and we cannot add anything in them, we cannot reprogram them. So we need to develop tools independent from those devices. And so one of these tools can be intrusion and anomaly detection, and this is what our work is about. So I will present the system. You're missing a part. I will present the system. The system is the substation automation system. So it's basically all the systems and networks involved in automation operations of the power grid. The communication architecture used in such a substation automation system follows IEC 61850 requirements. And so here is a typical IEC 61850 communication architecture. You have 3 levels. The base one here is the process level, so where you have circuit breakers and other machines. And you have measurement units on those machines. The second level is the bay level, that is the actuators. We call those devices, we call them intelligent electronic devices. Actually, they are ICS, so industrial control systems, dedicated to substation automation. And the third level is supervision. I also call it SCADA. The previous speaker, Mr. Ben Aloui, said the SCADA was all of it, but if I use the term SCADA, I will refer to the supervision level. So there are 3 protocols involved according to the units exchanging information. Measurement unit will will send their measurements to the IED through sampled values protocol. The IED communicates with each other using the GOOSE protocol, so that's the one I will talk more deeply today. And GOOSE means Generic Object-Oriented Substation Event. And the last protocol, the MMS, Manufacturing Message Specification, is for the communication between supervision and the actuators. So all those protocols are based on Ethernet. GOOSE and sample values are multicast protocol because they have a real strong real-time constraints. For example, the GOOSE protocol end-to-end transfer time must be less than 4 milliseconds. So this is why it is directly mapped on the Ethernet link layer. But MMS is based on TCP/IP because there are not such real-time constraints. Okay. So the GOOSE frame structure is standardized. I give it here to you. I will just detail the fields that are interesting for us. So this is basically an Ethernet frame. So you start your frame with destination address and source address. And the most interesting part is the PDU. The application protocol data unit of the frame. So the field that are interesting are the GOOSE control block reference. That is the name of the GOOSE message. It defines the transfer parameters. Then comes the time allowed to live. That is the time the destination will wait before considering the connection as lost. The dataset identifies the data to be transferred. GOOSE ID is the name of the GOOSE message. It's unique in the whole system. T is the transmission timestamp. State number. So state number is incremented every time a data of the dataset changes and requires to send a GOOSE message. And sequence number is set to 0 when a state number is incremented. And then when the message is sent over and over, it will be incremented for every iteration of this message with the same content. I will explain it a bit further. I must mention also the security field, which is defined in the standard, but the standard doesn't give any further explanation about the use we must do of it. And actually, for instance, the IEDs we have on our experimental platform, Siemens Ciprotec 5 line, do not use this security field. So, as I mentioned, GOOSE is a multicast protocol. It means that there is no acknowledgement of reception. To make this protocol a bit more reliable, there is a specific transmission mechanism. So when you have a data value change, there will be a new GOOSE messages sent here. So this is what I call event. Basically, it's the change of variable value. So we have a GOOSE sent here. First, it will be sent at a very high frequency, so T1, and then this frequency we divide it by 2, and so we go at a slower pace, T2 and then T3, until we reach stable conditions, and we have a normal pace of frequency T0. So those frequencies depend on your devices and can be configured. Okay, so that's it for that. Here is communication architecture. It's basically the same as two slides back. You have your process, your ICS, that is Intelligent Electronic Devices. You have the Ethernet IED supervision link. So here is IED supervision communication. And you have this Ethernet link for GOOSE protocol. So that is IED to IED communication. And so we added on this communication architecture, we added our detectors. I will detail a bit later. We added a module to check the bandwidth, to verify there is no Ethernet storm. And we added a module to detect corrupted GOOSE messages. So how does it work? The bandwidth checker works as a Modbus server, and it will send the SCADA works as a client, as a Modbus client, and it will get results of the bandwidth checker periodically by polling. And the corrupted GOOSE detector works as a client Modbus client, and it will send alarm to the SCADA only in case of alarm. SCADA will transfer this alarm to the IED. So in normal mode, when an IED receives a GOOSE, it will wait for an alarm from the SCADA, and if it doesn't come after a detection time, it will process the content of these GOOSE messages. But if during this waiting time the IED receive an alarm from the SCADA, they will enter a safe mode, and they will process some alternative programs and stop using the GOOSE communication, stop communicating with each other until the alarm is passed. So our bandwidth checker, it's basically it's a Linux module, ifstat. I'm sure a lot of you know about it. And so we modified it to be able to communicate its results to the SCADA. And it lets us to measure instantaneous and also instantaneous bandwidth, and also the bandwidth on a certain duration we can configure. I won't detail it further because I think the other one is more interesting, and I'm not sure I will have time to detail it, but if you have questions, feel free to add them at the end of the presentation. So this is about the detector of corrupted GOOSE messages. So this is the transmission timeline in a normal case. So it's the same than I showed you earlier. But we can imagine that at some point there is a false GOOSE messages. So here and here you have the same timeline, but here all those events are legitimate. All those messages sent here are due to legitimate events. But here, the system is supposed to be is in stable condition. So that is, this message, and this message are the same. And an attacker uses time slot during two two legitimate message to send a false one with a false content. For example, to take control of a circuit breaker or of another device of the process. And actually, we can detect that because even if the attacker is very good and the attack is perfect, so it means he will take care of changing the counters we have in the PDU of the GOOSE message, that is the state number, the sequence number. So here, he will take care of incremented the state number of the dataset, and he will take care of resetting the sequence number to 0, and then increment sequence number here and here. But when the next legitimate message arrives, it will be detected because there will be inconsistent sequence numbers. So here is the algorithm of our GOOSE messages, fraudulent GOOSE messages generator. So it actually it's based on SCAPI. It's a Python script. I didn't did it from scratch. I used some work of Hoyos. It's a researcher from Boulder University. And I put the reference in the paper if you are interested in getting it. So the SCAPI master will sniff all GOOSE messages, and it will decode them. And I decided to change only some variable, some Boolean variable. So if the dataset has a Boolean variable, it will just switch its value. It will modify the state number and the sequence number appropriately, and it will encode the fraudulent message and send it again. And now about detection of that. So the detectors is based on TCP dump using libpcap. So libpcap functions sniff the traffic on the network, and okay, and so this detector, so its configuration is based on the configuration file of the ICS. So when you configure your system, your whole system, you generate some configuration file describing the system, its architecture, its communication architecture, who is supposed to communicate with who, what kind of messages will be sent, etc., etc. It's very precise, so we can use them to define what is acceptable in terms of communication in your system. And then, according to these references, we'll check for every entering GOOSE messages if this GOOSE message is actually in the authorized list of GOOSE messages, if transmission time is coherent, if your counters, state number and sequence number are coherent, and we will just display the results on your console. So here are the results from this detector. So the first two messages, those ones, are legitimate ones, actually here. The first two are legitimate. So you can see that state number is one here and one here. So that's the first change that occurs in your dataset that generated these GOOSE messages. And the sequence number is 1140, which means it was 1140th time we sent these messages over the network. This is the next one. And here our fraudulent GOOSE message generator sniffed this message and changed the Boolean value in it. So it updated the state number accordingly, telling, hey, this is a new state, our value has changed. And this is the first time we send this information. But after a few seconds, after 2 seconds, which is the T0 time, we have a new legitimate message. And this is where the detection can be made. Okay. And this experiment was made on the GEEX platform. So GEEX is for Greener Industrial Control System Sandbox. It's an experimental platform at the NCCube, the engineering school of Grenoble INP. And if you want more information about it, feel free to ask. We have a lot of PLC, HMI, every kind of industrial control systems, a lot of softwares associated to them, and some prototyping boards as well. And for this experiment, I used the Cyprotex 5 devices of Siemens. So here is the conclusion of this presentation. So I presented you the whole architecture, which is that. But here in this paper, I just explained the two detectors of attack on the GOOSE network. It's ongoing work, so it's not completed yet. And so I still the detectors are implemented, but the whole architecture is not as a whole yet. Okay, I'm done. So if you have any questions, it's time for you.
Do we have any questions? Thank you, Maël, for an interesting talk. A question here.
Thank you. How do you prevent how do you stop the GOOSE communication after the attack is detected?
How do we stop it? What do you mean? You mean?
How do you block it? I think.
Oh, here? You
yes,
mean?
Here, yeah.
When I say that I prevent IAD from communicating with each other, it's in the program. It's just we run. You can program logic into those devices, and so when they receive the alarm from the supervision, they will switch from program, and in the new program they will execute. There is no involvement of GOOSE messaging. That's it.
Thank you.
Any more questions? I guess not. You can always contact Maël after the talk.
Sure.
Thank you very much. Please give her a hand.
Thank you.